Oh my God, we are in week 12, guys. Week 12, that is 75% of the way through the course. We're almost there. Okay, the second good news that I have for you is that this week is rotational kinematics, and the truth of the matter is you already know everything for this week, okay? You did linear kinematics and you did a great job at it, and now we're moving on to rotational kinematics, which is the same thing. We just change all of our linear variables to rotational variables. So for example, let's say that in the linear world you have this little amoeba that's like, starting out from rest and then accelerating. We want to find out its speed after it accelerated for like 3 seconds, right? That would be linear kinematics. But what if we had like a merry-go-round or a CD that started from rest and started rotating a certain number of degrees? What would be its rotational speed after a certain number of seconds, right? We're just switching what we did in the linear world into the rotational world. All right. With that said, let's go to the quote of the week. This week's quote of the week is from a Vietnamese spiritual teacher named Thich Nhat Hanh. And he said, "Many people are alive but don't touch the miracle of being alive." I officially really understood this after I took my first biochemistry course. I am a physics guy and I have a physics background, but I have taken organic and biochemistry also just so that I can, be better at teaching physics to, pre-med and biology folks. And so I realized in a way that I never understood before when I took this biochemistry course that there are so many trillions of things that the body is doing at every single instant in order to make it possible to be alive and to function and to interact with the world the way that we do. And that is crazy. But the thing is, what happens is our minds are these big filters, right? Like if we were always looking at the world and looking inside of ourselves and saying, wow, how amazing is this? How beautiful is this? How sacred is all this, right? If we were always doing that, we would get distracted. We wouldn't, get done what we need to get done, and we'd probably get eaten by something in the woods, right? But if we live life so that we're only ever filtering and that we're always just focused on exactly what we need to do at any given moment, then life gets hard, it gets boring, and we start thinking we need to worry about everything, right? Because if the only thing that matters is what we need to worry about in order to survive, then life really shrinks, right? So I think that we should take a little time to remember that we are alive and that being alive is a miracle and that our bodies are doing such a tremendous job right now to make us be able to be who we are and do what we do. And that appreciation, I think, makes life a little bit more rich. I also think it's freaking amazing that we came through the universe, right? The universe has developed us, right? It has these certain laws, these certain elements, right? And all those elements and those laws converge to form life that we know it, right? And that life is able to then see, witness, and study the universe. So in a way, we're like this clever little trick that the universe used to be able to be aware of itself, to be able to study itself. Because we can't be separated from the universe. We are the universe. And that's pretty cool. All right, enough philosophizing. Why do we care? If you guys could go to that slide. I don't know if you've ever seen Simone Biles do a floor routine or any gymnastics before, but it's freaking amazing. Not only is she just capable of superhuman things, just watch one of her floor routines. She gets high up in the air and spins and flips in ways that I don't think a human should be able to do. Secondly, she's such a competitor. Like the focus and the confidence and the unshakable confidence that this girl has is mind-blowing. I wish I had 10% of it. But here's the deal. She does these floor routines, and imagine that she's doing this tumble in the air, right, where she is increasing her angular velocity from 3 to 5 revolutions per second while rotating through 1/2 of a revolution. How much time would such a maneuver take? After this lesson, you'll be able to solve this problem using rotational kinematics. Okay? And now I would like to tell you the best thing about rotational kinematics, and that is that you can steal everything that you learned from linear kinematics. Okay? So all the variables that we used in the linear world now translate to analogous variables in the rotational world. So what do I mean by that? Well, all right, let's look at the linear world. What were our main variables? Well, we had distance, or x, right? Okay, that's linearly how far we went in meters. We had velocity, which was in meters per second, right? So I'm just going to put an m here for meters. And this is, how much ground, how much distance we covered in a certain amount of time. And then we have acceleration, which was the amount with which our velocity changed, right? So meters per second, how the rate at which our velocity is changing, okay? And so these have direct analogies in the rotational world, okay? So distance, for example, if instead of moving in a straight line and covering a certain number of meters, you're now rotating through a certain number of degrees. So distance becomes theta, right? How many degrees are you rotating through? And specifically, this is the one area in physics where we instead of being in degrees, we actually want to focus on radians. So how much are you turning in radians? Okay? V, our velocity, turns into angular velocity, or omega. Don't call it a W. It's one of my pet peeves. It's not a W. It's a Greek omega. And this is radians per second, right? So how many radians is this object turning per second, okay? And then acceleration just turns into angular acceleration, and that turns into a Greek alpha, right? And that's going to be, big surprise, radians per second squared, okay? So how cool is that? You get to basically do the same stuff. It's going to be the same laundry list, the same equations. You're just, every time you see a D, you're replacing it with a theta. Every time you see a V, you're replacing it by an omega. And every time you see an A, you're replacing it by an alpha. Okay? If you guys could go to the next slide, the one that says angular displacement. So this basically focuses on these two right here, the linear displacement versus angular displacement. Obviously, in the linear world, we're moving a certain number of meters. And then it shows here with the CD that in the angular world, you're moving a certain number of rotational radians, okay? And that is going to be delta theta, right? How much you're actually moving in radians, okay? Sometimes angular translation is given in revolutions, or angular velocity or angular displacement is given in revolutions instead of radians. How do you convert revolutions to radians? I think you know the answer to this question. Every revolution is how many radians? 2 pi. So I'm going to write this right here. 1 revolution is equal to 2 pi radians. So there's going to be problems where it's going to say, RPMs, like revolutions per minute, right? And you want to be able to convert that into radians if you're going to be in the SI units for the rotational world. So remember that. In fact, most problems, if you see revolutions per minute, revolutions per second, revolutions per hour, whatever, immediately convert to radians. Never hurts. Okay. All right. Next up on the next slide, it says angular velocity. So just like you can have a linear velocity, right, the amount of meters you cover in a straight line per second, you can also have an angular translation, which is the number of radians that something turns per second. All right? And these two pictures, once again, kind of illustrate the difference between the linear and the angular world. In the angular world, you have a fellow who is spinning around at a certain angular velocity, right, a certain angular speed around a gym pole. Okay? And then lastly, you have angular acceleration. Same goes for angular acceleration. In order to reach a certain angular speed, you must undergo an angular acceleration. So once again, a CD, let's say, starts out at rest, and then it speeds up, right? So it has a high angular acceleration to get it to whatever angular speed you need to read the CD or DVD. And so the next slide, what does this all mean? Well, this is the best part. Where is my eraser? I don't have one. Will this work? Maybe. I don't know. Probably good enough. This is embarrassing. Oh my God. It's taking so long. Okay. All right. Almost there. I don't know why this thing just disappears sometimes. Where does it go? Okay. All right. So what does this mean? It means that whereas our old kinematic equations were, V2 equals V1 plus AT, and D equals V1T plus 1/2 AT squared, and V2 squared equals V1 squared plus 2AD. Now, these can all be translated into rotational kinematic equations, where we say that omega 2, right, the final angular velocity is equal to the initial angular velocity plus the angular acceleration times time. This guy will turn into the angular displacement, or delta theta, equals omega 1 t plus 1/2 alpha t squared. And lastly, this will turn into final angular speed squared equals initial angular speed squared plus 2 times angular acceleration times angular displacement. Okay? And then you solve it the exact same way. You're going to have laundry lists, and you're going to find what variables you have, what you need, what equation you want to use, and solve for the variable you're looking for. Okay? In the next video, we're going to begin doing some examples. But for now, just rest assured, you already know everything you need to do for this chapter, and you're prepared.